Hello, everyone. Many thanks for being here today. We are privileged to be with Professor John Bischof. He is the Office of Academic Clinical Affairs Senior Research Advisor for the Office of Discovery and Translation Grant Programs. He's also a distinguished McKnight University professor and a faculty member in the departments of Mechanical Engineering and Biomedical Engineering. He's also the director of both the University of Minnesota Institute for Engineering in Medicine and the NSF Engineering Research Center for Advanced Technologies for Preservation of Biological Systems. He also holds the Medtronic-Bakken Endowed Chair for Engineering in Medicine. We are privileged to have him here. He's also a renowned researcher in thermal bioengineering, having contributed to applications in therapeutic, regenerative medicine, and diagnostic. He has received international attention for his research focusing on biodistribution and heating properties of gold and iron oxide nanoparticles and other biomaterials. So I'm not going to make you wait anymore. John, again, many thanks for being here, and the floor is yours.
Thank you, Dr. Kashar, Patricia, for the kind invitation, and thank you all for your attendance. I will go ahead and share my screen. And I will tell you a few things about what started off as research in my lab and then transitioned into a small startup called Vigilant Diagnostics. And so it's kind of a long title, but a breakthrough in colorimetric lateral flow diagnostics, and then a light emitting diode LED-based handheld thermal contrast reader, which is kind of like the evolution of this technology, which I think is pretty exciting, particularly in the LFA space or lateral flow space, because this is the cheapest, simplest, easiest to use, most ubiquitous diagnostic in the world. And with the use of this reader, one gains tremendous amount of sensitivity, but also quantitation. So it really changes the game for the LFA, which used to be like a yes/no answer to something that could be more akin to a lab-based reading. So I'll be happy to share that story with you. But before I go through that, I wanted to tell you just a few things about the Institute for Engineering and Medicine. This is actually a collaborative effort between the College of Science and Engineering and the medical school. And we have quite a bit of research. We help groups go after larger center grants. We also do quite a bit of education and training, and a tremendous amount of industry engagement where we're bringing engineers to be in contact with clinicians, as well as clinicians in contact with engineers to do more in the bioengineering space. And we also do this very much in partnership with our great biomedical engineering department here on campus. And I also wanted to bring to your attention, in case you hadn't heard yet, and this is a diagnostics biosensing group that Patricia's put together. We are really going to be privileged in the fall to have on October 14th, Stephen Quake, who's the head of science. Well, his title is actually changing to Chief Advisor of Science in the Chan Zuckerberg Initiative. And he has done a tremendous amount in terms of DNA-based diagnostics and DNA manipulation and instrumentation. And he's a physicist who's worked in the biomedical space. So we're really, really excited to have him. He's in, I think, every single academy there is. And so he will be giving our Otto Schmidt Distinguished Lecture in the fall, and I really encourage you all to attend. So IEM works in a lot of different areas. I'm not going to go over all of them, but I just want to mention that we do have these events like the Otto Schmidt. We work on centers and research funding, but we also work on engaging clinicians and engaging engineers to work together. The clinical immersion program is one that actually embeds engineers from local industry and also national industry into our surgical suites to see how devices are used, and then to actually do to iterate and design on the fly while observing how the devices are being used. So it's really fantastic. We also do STEM pipeline events where we're actually reaching out to K through 12 kids from across the state, getting them to begin to think about a potential career in engineering and medicine or other STEM fields. So if you have an interest around IEM, I encourage you to visit us. We're just iem.umn.edu. And with that, I'll give you my disclosure about Vigilant, because it is a startup out of the University of Minnesota. It actually, in some sense, that's also what IEM does, is it the Bakken Medical Device Center is a part of also IEM, and it's really about creating more of a startup culture at the University of Minnesota. And so Vigilant is one of those startups that have come out, and there are many that are coming out of the University of Minnesota all the time. So I have equity and royalty interests, so does the university, and these are reviewed and managed by the university in accordance with their conflict of interest. Great. So what are these lateral flow assays? I think everybody's probably used one of these during the pandemic, for COVID. It's a huge market. It's used for clinical analysis, toxins, pathogens, pesticides, et cetera. And infectious diseases is the one that's the most obvious, that we've all heard about because of COVID, and we probably use something that even looks like that LFA you see there. The advantages are the speed. Usually you're getting an answer within, minutes, 10 minutes, usually, not always. You can actually go out for longer periods of time, like even out to half an hour, and you tend to get higher sensitivity with that, but people don't want to wait a half an hour. So some of the weaknesses are that it is qualitative and has low sensitivity, but it is low cost and it's very simple to use. So some of the key applications you see there around pregnancy, malaria, TB, these are all examples, except for the last, of infectious diseases, troponin being one that tells you about cardiac events and infarcts. So it's a big deal, and we've all used these strep tests, flu tests, et cetera. But what this talk is going to get into is like, how can we make them better? How can we stretch them to be a little bit more like a lab-based diagnostic, and maybe address these weaknesses of being qualitative and low sensitivity. So yeah, again, the lateral flow assay dominates point of care, has done so for many decades. They're about 1,000 times less sensitive than an ELISA lab-based test. And this is kind of what it looks like. So it's basically paper. It's a paper-based diagnostic. The membrane of the lateral flow assay is nitrocellulose. It's designed, you can get it to be of varying thickness and varying types of pores. Those pores determine how fast your sample, that little droplet on the left, will flow through the test. So smaller pores, it flows slower. Larger pores, it goes faster. And you have then, a conjugate pad here that releases the gold nanoparticles that will go into flow. You have antibodies that are on the test line. You also have antibodies on the control line that will capture either the antigen and do basically like a sandwich assay. And I'll talk about that a little bit more, where the antigen on the test line binds the analyte of interest, and then you have, or the antigen, and then your gold nanoparticles, which you see here, they also have antibodies on them, and they would sandwich, as you can kind of see down here in the pictorial of what's going on in the test line. And so that is what you will read as a colorimetric, yes, no, the antigen is there or it's not. And there's a number, the membrane itself I talked about, and then the absorbent pad really just helps the flow move through the lateral flow assay. So it's not a terribly complicated diagnostic, but there are lots of ways to make them not work well. If you don't have a good membrane, you don't understand your antibody very well, you don't have the proper blocking chemistry, et cetera. There are a lot of different ways to make these not work well. And so there's a certain refinement and respect that's needed when you actually build one of these. And so there definitely is a difference between well-built and not so well-built lateral flow assays. And this graph here is kind of showing, this came out in ACS Nano. This was an invited review or perspective article that's pretty highly cited. So anybody who wants to know more about the LFA market, I really would encourage you to look up this paper. So Lou is the first author. I'm in there somewhere. And this graphic has shown up in a lot of different places now because it really shows you the regime in which we're trying to operate for lateral flow assays, but then also where things are pushing, also the lab-based ELISA and PCR and digital ELISA and so on, that's all shown there as well. And what everybody wants to do is to increase analytical sensitivity without giving up the diagnostic speed. So we want the speed of the LFA of today, which is minutes, but then we want to get the analytical sensitivity of the lab-based work, which you see down on the bottom, which takes detection time and diagnostic speed. That's your cost, so to speak. So this future point-of-care diagnostics in the upper right-hand corner, that's where everybody's trying to get to. And if we can get there with an LFA, that would be fantastic because they cost literally, less than $1 to make, each one of them. Okay, so thermal contrast amplification, what is it, and how do we apply it to the lateral flow assay? Well, it turns out that a colleague of mine, who's now a dean in Singapore, his name's Warren Chan. He's very well known as a chemist and biomedical engineer working on gold nanoparticles. And so, more than a decade ago, we started talking about how people were working, many different groups were working on plasmon effects, basically how lasers and light interact with gold nanoparticles and how you can use that to do various things. The really charismatic application of the day was to actually treat cancer. So if you go back to the early 2000s, you'll find a lot of really highly cited work. One of the papers that I remember well was coming out of Naomi Hallis and Jennifer West's lab, where they showed that they could use a shell, like the middle example of a gold nanoparticle, which pushes the absorption into the near infrared to treat cancer. And so they were actually injecting these gold shells intravenously or interstitially into cancers and then irradiating with near infrared. And you might say, well, why would you do that? And why wouldn't you want to just use a gold nanoparticle that's on the left, that's in the visible? And the reason for that is that the near infrared doesn't interact as much with water. And, we are comprised, human beings, skin, et cetera, lots of water there. So there's a lot of chromophores that will absorb the laser and attenuate the laser. If you go to near infrared wavelengths, you can actually penetrate deeper. So you can do it with a shell. You can also do it with a rod, and a lot of different labs have looked at different ways to do this, where you push the absorption using near infrared. What Warren and I talked about, certainly about cancer, and this is a very nice review that gets into that. Zhangpeng Qin wrote this in Chemical Society Reviews, also pretty highly cited. And then also there's work even earlier than that in the Journal of Physical Chemistry talking about these different absorption regimes. But what the lateral flow assay is made of is basically the colloidal gold. And so it picks up in the visible regime. And so that is basically where you're matching the wavelength of the laser with how the gold nanoparticle is designed. And because of this plasmon resonance, which is an interaction with the electron cloud in the gold, you get a tremendous absorption and resulting heat. And so we decided, Warren and I, to work on just the gold nanoparticles on the left that are already in 90+% of the lateral flow assays and figure out how to visualize them in the test line and see what we could do with that. And so this is a simple equation. It's basically saying the heat Q is equal to the number of nanoparticles N times what's called the absorption cross section. And that's just like a design parameter that says how well the gold is going to actually absorb the laser that you have picked, whether it's visible or near infrared, times the fluence of the laser, I. And what we showed in an early paper in 2012 is that if you look at optical density just by going into a UV vids with gold, gold shows up basically red. And you can actually see that. And as you dilute down the gold concentration, you can see less and less red, or as you go up, you get more and more red. And you can actually quantify that. If you do it thermally, so we actually have over here on the left, these are droplets that have gold nanoparticles in them. And we're irradiating those droplets with, in this case, it's a visible laser. And what you can see is that at some point, you visually can no longer see the gold nanoparticles, but you can see the thermal signature of the heat that's being evolved from the laser interacting with the gold. So that gives you, roughly, let's say, 2 orders of magnitude in this very simple proof of principle. So you're about 2 orders of magnitude lower in terms of what you can detect with a thermal contrast versus optical. And so we started looking at this more carefully and thinking about how we could use that in the test line of a lateral flow assay. And so here you just see a schematic of that. So it's a green laser irradiating the test line. And, we don't need to irradiate the control line because we can see that very clearly. But it's the test line where it's like, okay, well, are you positive? Are you not? Are you subvisual? Is it possibly you are like you have COVID, but the test line is negative? So that would be like a false negative. Is there a way that you could shine the green laser and actually see that? And so this is an example of doing that with cryptococcal meningitis. This was done in collaboration with David Boulware here at the university, who's become quite famous in this area. And what you see is, on the S2 here on the left, you can see a very clear test line and you get a very strong thermal signature. If you take the control negative strip, you get a very small signature that has to do with basically background heating of the LFA membrane. And then S1 is your value add, right? So you are visibly negative, but you get a strong thermal signal. And so here's an example of doing a dilution study with cryptococcal meningitis lateral flow assays. These are made by IMI. And you get, certainly more than an order of magnitude improvement in your ability to detect the disease. And it also widens the analytical range of what you can do with the lateral flow assay. So this was exciting. And so we decided to look at other infectious diseases and did a whole bunch of different infectious disease dilution assays. So dilution assays are pretty simple. You start with a positive control, and then you just start doing double, essentially halving the concentration by adding more buffer. And then you're taking a droplet of each of that, and you're using the manufacturer's recommended approach to the lateral flow assay. And then you look visually to see whether you have a test line or not. And then you also look at a thermal read. And so this will tell us whether we're able to go subvisual or not, which means you're extending the analytical range. You're also catching those false negatives. And that was the intent. And so here are some examples. This is a fairly well-known lateral flow assay made by BD, which is, in fact, the reader there is probably like the #1 reader at least it was the #1 reader on the market, called the BD Veritor system. And, but you can see that they're using it as a plus minus still. It's still being used as a qualitative measure of whether, you have or do not have the disease or the antigen in your sample. You can see the dilution on the top as we went down in dilution from clearly positive on the right to, who knows, your subvisual. And with the thermal contrast, we were able to go all the way down, 8-fold at least below visual. And then, of course, you have your negative control. So we repeated that with malaria. And this was really interesting. This was actually a collaboration with a group that worked with the WHO. And if you look on the right, this is actually something that's handed out, the performance metrics for malaria rapid diagnostic tests, or RDTs, which is essentially, they are all LFAs. And I'm pointing out the one that we used, and it's very high up, and it's called First Response Malaria HRP2, close to the very top in terms of their panel detection score. And you can see as you move down the list of more than 30 of these, you get to some that are quite not very good at all in terms of their ability to, detect. And it's just an unfortunate truth that not all LFAs are made well. So we were actually working with a very well-made lateral flow assay, and you can see these. This is P. falciparum, and so this is one of the various strains of malaria, and you can see the positive test here that again goes subvisual, and we are again able to go about 8-fold below that for HRP2 in this work. We then tried something else with David, which was very interesting, and basically, could we use this to detect antigen burden in a clinical cohort? So David is constantly in Africa running clinical trials, and he will bring back the lateral flow assays that he used, but he also has other measurements of the cerebral spinal fluid from some of these patients that he can compare to by PCR and other laboratory methods. And so what he did was with us is basically lateral flow assay was, we looked at the thermal contrast, but then we also looked at a laboratory, LFA titer, I'm sorry, a predicted titer that came from a separate laboratory test compared to the thermal contrast, and you can see that you get a very strong correlation. And so what this suggests is that in the future, once we have readers that can be used in the world for, malaria elimination or cryptococcal or whatever, that you could imagine making a measurement and actually making a clinical decision based on whatever the quantitative measure could be of your particular infectious disease. So Dave is still very interested in this, and he's waiting for us to give him a reader, which we are hopefully very close to, that he can actually begin to use in the field and actually make, hopefully, life-saving decisions based on this kind of new information. Another example of what you can do is in the case of strep. So we've all had, well, most of us have had children who have had strep or know children who have had strep. And one of the things is that there's a lot of confirmatory testing that's needed. So a lot of times, you might come in with symptoms. The child might come in with symptoms, or the adult, and the LFA will not, the LFA will be a false negative. Then they'll swab and they'll get a culture, and 24 hours or whatever later, they'll let you know, oh yeah, indeed, you need antibiotics. What this is saying here is we did we took the lateral flow assays from a series of people that came through a clinic, and we asked the question, okay, of those that were negative, how many of them were false negatives? And we could compare to the, we were able to compare to the culture. And then we also had negative controls. And what you could see here on the right bottom is we were actually able to find 50% of the false negatives without even changing the lateral flow assay at all. So there's no improvement of it. We just read it with a thermal contrast. So that was another interesting example of what you could do with an improved reader for a lateral flow assay. We also tested wet and dry, and we were able to show the same trend for both. So this leads to an interesting concept, which would be, well, what about optimizing the lateral flow assays so you can actually work with thermal contrast? So in other words, instead of just using a lateral flow assay that's been manufactured by a company for visual use, so qualitative and not very sensitive, what if you actually were to design a lateral flow assay where you made all the design decisions around membrane, size, shape, or whatever of the gold nanoparticle, and all of the antibodies, the buffers, etc.? Would that give you a better read with the thermal contrast amplification? So it turns out that there's a lot of different ways of doing this, and this is part of that review article I mentioned from Yilin Liu. You can certainly optimize the LFA itself. There's lots of things to do there in terms of the blockers, detection molecules, capture molecules, etc. You can do sample enrichment, but that adds steps. So there's a lot of reason why people don't want to add concentration, because it takes the simplicity away. You can do pre-amplification. So there's nucleic acid LFAs that are using that technology right now. You can also study the kinetics and the reagents that are used directly in the lateral flow assay. So this is basically the chemical kinetics and the binding on the test line, and really look at the Peclet number, convection versus diffusion, and the Dalton reaction rate versus diffusion rate, and optimize that. And then you can look at chemical enhancement. There are lots of different ways of doing that. Examples might be using silver enhancement. Of course, that takes away the quantitation ability, or the label design, which we've already talked about, maybe making the GMP, the gold nanoparticle, a different shape or size, and then different readers. So we are doing a thermal reader, but there's lots of different groups out there that have looked at, fluorescence and magnetic and electrochemical, et cetera. So there's a lot of different ways of doing this. And so we're focusing really on the thermal piece, but there are overlapping optimizations that can be done within the lateral flow assay for all these technologies. So what we did was we actually took the gold nanoparticles that are used in the lateral flow assay, and we basically just use larger gold nanoparticles. You can also use different shapes, and you can also get enhancements that way. But the size ended up being a really powerful way of doing it, because it changes that absorption cross-section or design parameter dramatically. And so you can look at the analytical sensitivity on the bottom right. This is actually a review article that came out of Warren's lab, and you can see the lateral flow assays are like the worst in terms of their sensitivity versus ELISA, PCR, fluorescence, SIRS, magnetic, et cetera. And with TCA, we were able to show that we could hop about 3 orders of magnitude just by using better gold nanoparticles. And better, I mean, like designed to enhance those detection thresholds. So then we use that to design, actually, we went past ELISA and we went to PCR level sensitivity for SARS-CoV-2. And this was just like a really intense optimization exercise with Jim Sackerson, who worked with Yilin. Yilin was finishing her PhD in my group at the time. And you can see that we actually pushed right down there to that little yellow diamond. And as I said before, you can actually get pretty good binding if you slow down the flow, because it gives it more time for everything to diffuse to the reaction site on the test line. So a half an hour is like, probably nobody wants to wait that long, but this was a demonstration basically that we could get into that femtogram per ml or attomolar range, which is basically where you go with PCR at the time. So we've done a lot of different things with the TCA technology. We started just demonstrating that there's a reader and that you could get basically an order of magnitude enhancement. We did work around showing that you can do this multi-site validation with David Boulware, that, you know, basically a clinical cohort. The TCA signal went with antigen burden in the patient cohort, as well as catching a lot of those false negatives that I mentioned for the strep. And then we were able to hit ELISA level for both HIV, P24. That was a collaboration with the CDC. A guy named Timothy Grand, who actually is retired, but Zhirong Wei is still there. And then the role of the nanoparticle design basically in building a better LFA4 thermal contrast, and then even getting all the way down to PCR level, which is something that a lot of people have interest in. And then we've got, you know, patents and a variety of funding that we've had over the years for that. So now I just want to bring you up to date where we are today. And it's really been, this is the last piece of our story that's really about the reader technology, trying to get it to a place where it can be turned into a relatively cheap device, you know, medical device that could be used around the world. So the concept isn't that difficult to understand. So we have a lateral flow assay. You shine a laser onto the test strip, and then using an infrared camera, there are other ways of doing it, but IR seems to be the simplest one. You get a thermal signal, and that test line versus background is that's your readout. So we've had these different laser-based systems over many years now, starting with the one that you see on the left upper, which is essentially, you know, on an optical board in the lab. You know, everything's open to the environment. It's great for doing work and publishing papers, but there's no way anybody can use that. We stuck it in a box, and that helped, and we added some lab view control to that, and then we moved on to another box that was actually built in China with InnoMB, which was a collaborative group, and then you can kind of see an LFA scan result there on the bottom. So this is that was great, but we were still looking at something like 20 minutes per read with the laser system, and it was a little bit difficult for people to do repetitive measurements with those thermal contrast devices. So then there was this big breakthrough in 2024. Tomo Sato, who's the chief technology officer of Vigilant, the little company, which actually started back in 2014. He's basically showing you here a concept around using a light emitting diode to irradiate the lateral flow assay and then read with an IR camera the entire region where the lateral flow assay was irradiated. So they're not just using a laser to, you know, the laser beam is usually about, you know, it's a sub-millimeter, and it's interrogating a lateral flow assay test line that's also like maybe 2 millimeters thick. So you're only interrogating a piece of that line. This new approach with the LED reader is basically interrogating the entire test line, and it's doing it in 2 seconds, and it gives a quantitative digital result, and it's also very cheap because the LED is a lot cheaper than the laser, and there are like no moving parts. So this has like been a huge breakthrough for us. And these are just some example readouts. We've gone beyond these types of readouts now, but you can kind of see it's basically, you know, you get a positive, a negative on the right, and then there's a consult where you're maybe in the middle. You know, it's possibly there's something above background, but you need to look at it more carefully. And so this is just some data where, you know, it shows you where the visual read ends and the TCA is able to go beyond. And then it also shows you here the reproducibility across multiple dilutions. So these are multiple groups of strips being read at the same level of dilution. And you can see, yes, there's a bit of an error bar, but it's not bad. And you're getting, you're tapering off, and you're certainly getting below the visible limit. In terms of repeatability, this is looking at the same strips over and over again. You can see that the LED is actually an improvement over the laser as you are at certainly at the higher levels, and they kind of come together. And so this is what the LED reader looks like now. This is what we're calling our alpha prototype. So it's about 6 inches wide and almost 4 inches tall. It has little feet, and it's about a foot long. And there's a little this is the only part that moves, and it moves because you pull it out. So it's under your physical control. This plugs into a Windows PC, and with proper drivers and software can basically read an LFA in like 2 seconds. So this is a little bit of a breakdown. This is the piece that would have the LFA, and then that's basically injected into or moved into the entire system, and you can see some of the optics here that are governing how the LED is reading into ultimately an IR camera, a very simple one. This is some of the performance validation work that we did. You can see again, this is using HCG, so this is a pregnancy dipstick, and control line, test line dropping off, so you can't really see where the visual ends. Here's 1x and 1/2x in the dilution, and you can kind of see where that's at. And this is what we're able to capture still, and you've got pretty good, this is mean plus or minus three times the standard deviation. So we've got pretty good reading using the LED TCA on that dilution study. So the green is the mean, and the red bars are the 3 times standard deviation, and 4 repeats each, 4 samples measured 4 times each. And then with reliability, this is mechanical reliability, so 3 reads after removal and insertion of the same sample, so reinsertion, and they're pretty tight. And then also initial assessment of intrasample variability by 3 samples at half the visible threshold with 3 readings overlaid, also pretty tight. So this is where we are with our performance data. And so a couple of thoughts, maybe just to sort of wrap this up. It really doesn't take as much cost. It's like a lot cheaper than the laser. It does take more optical power, but it's become something that could truly be a handheld. Currently, it's not quite a handheld, but it could be. The read time is seconds versus minutes. There's no motor needed, no moving parts needed, and the sensitivity is equivalent as I demonstrated. And we think probably a little bit better, honestly, with the LED TCA. So a couple of new ideas here about where this might go is flexibility in antigen targets and reagents. So it's possible that you could think about this in terms of being a universal enhanced LFA platform. And it could be, there's been so much work that was done around COVID in terms of antigen discovery and antibody, both antigen and antibody discovery, that it's becoming less problematic in terms of like the creation of new reagents to make LFAs in a very defined way. And you can actually then do more effective prototyping of final LFAs with, working with different reagents. Another possibility, and we've worked with Mark Osborne on this a bit, is around nucleic acid quantification. PCR is still what people are going to go to, but there is a possibility that instead of just running PCR out and however many cycles, and you basically get an answer that says, yes, there's something present in your sample, you could actually do it in a defined way where the kinetics were understood, and you could even use the nucleic acid LFA to tell you, after knowing how many cycles at what temperature, et cetera, how many copies you have, and you could even get to nucleic acid LFA quantitation. Metabolomics using colorimetric approaches are also under discussion. And Tomo has been working with Greg Bielman's group and others to think about this, for instance, around small molecules like succinate. So I think that's absolutely going to be a possibility that'll require a different form factor, because it's probably not going to be exactly an LFA. It could actually just be liquid, literally, that one would be looking at directly. So to acknowledge lots of funding partners, including the Minnesota Partnership for Biotechnology and Medical Genomics, NIH, and NSF. We had a STTR grant, several NSF grants, and worked with Bobby Pritt and Dave Boulware on this University of Minnesota Mayo Partnership grant, a Minnesota Futures grant as well. And then we've collaborated with a variety of different groups across the world on many of those LFAs that I showed, and some that I didn't. And then some really fantastic PhD students. Zhengpeng's gone on to his own career now at the University of Texas, Dallas, where he's a full professor. Yuru is in Shanghai working with the University of Science and Technology there. Lizan just started at Purdue, and Yilin's gone into industry. Last I heard, she's working for Micron, and we've worked with a variety of different really talented undergraduate students. And I really want to give a shout out to Tomo Sato, who is our Chief Technology Officer for Vigilant, who came up with the LED TCA concept, which has been a real breakthrough for this area. So with that, I'll thank you for your attendance and interest, and I would be very pleased to entertain any questions you might have.